Webb's glimpse of Alpha Centauri could rewrite the future of space travel? Imagine standing beneath the night sky, gazing upward at a single point of light that has captivated humanity for thousands of years. A star so close in cosmic terms that ancient sailors used it to navigate across vast oceans, and yet so impossibly distant that no human technology has ever come close to reaching it. Now imagine that in a single moment, everything we thought we knew about that star system, about the possibility of reaching it, about the future of human civilization spreading beyond our solar system, has suddenly changed. This is not a fantasy. This is not the plot of a science fiction novel. This is the reality we are living in right now, in this extraordinary moment in human history, because the James Webb Space Telescope has turned its golden mirror toward Alpha Centauri, our nearest stellar neighbor, and what it has seen there may fundamentally transform not just our understanding of that distant system, but the entire trajectory of space exploration, the timeline for interstellar travel, and the question of whether humanity will remain forever confined to one small corner of the galaxy or will one day spread across the stars. Tonight we will journey together through this remarkable discovery, exploring what Webb has revealed, why it matters so profoundly, and how a single glimpse of our cosmic neighbor might rewrite the future of space travel. Wherever you are right now, whether you are settling into bed after a long day, sitting quietly in a chair with the darkness pressing against the windows, or lying still with your eyes closed as these words wash over you, I invite you to let go of the concerns and tensions of daily life, to breathe slowly and deeply, and to travel with me across 4.3 light-years of space to a star system that may hold the key to humanity's greatest adventure. Before we embark on this journey, if you find value in these explorations of cosmic discovery, a gentle subscription or like helps this channel continue bringing these stories to you. And now, let us drift together toward Alpha Centauri and discover what Webb has shown us. The star that called to us. Alpha Centauri has been a beacon in human consciousness for as long as people have looked up at the night sky and wondered what lies beyond. From the southern hemisphere, this brilliant point of light shines brighter than almost any other star, a luminous guide that ancient navigators used to find their way across the trackless oceans. The indigenous peoples of southern Africa, Australia, and South America all told stories about this star, weaving it into their myths and using it to mark the changing seasons. To the ancient Greeks and Romans, it was part of the constellation Centaurus, the centaur, a mythical creature that was half human and half horse, representing the meeting point between civilization and wilderness, between the known and the unknown. But Alpha Centauri is not just one star. Through a small telescope, it reveals itself to be two stars orbiting each other, a binary system where two suns dance around their common center of gravity in an eternal cosmic waltz. These two stars, designated Alpha Centauri A and Alpha Centauri B, are remarkably similar to our own Sunday. Alpha Centauri A is slightly larger and brighter, about 10% more massive than the Sun, while Alpha Centauri B is slightly smaller and dimmer, about 90% of the Sun's mass. They orbit each other once every 80 years, sometimes approaching as close as the distance between the Sun and Saturn, and sometimes separating to about the distance between the Sun and Pluto. Then there is a third member of this system, discovered in 1915 by astronomer Robert Innes. This is Proxima Centauri, a small red dwarf star that orbits far from the binary pair, so far that it takes more than 500,000 years to complete one orbit. Proxima is much dimmer than the other two stars, barely visible even through a telescope, but it holds a special distinction. At 4.24 light-years from Earth, Proxima Centauri is the closest star to our solar system, closer even than Alpha Centauri A and B, which are about 4.37 light-years away. This entire system, all three stars together, represents our nearest stellar neighbor, the first destination that humanity must reach if we are ever to become a truly spacefaring species. The distance that separates us. 4.2 light-years sounds like a small number until you truly grasp what it means. A light-year is the distance that light travels in 1 year, moving at the cosmic speed limit of about 186,000 miles per second, or roughly 300,000 kilometers per second. Light can circle the Earth more than 7 times in a single second. In 1 year, light travels about 6 trillion miles, or roughly 9.5 trillion kilometers. 4.2 light-years means that Proxima Centauri is about 25 trillion miles away, or 40 trillion kilometers. These numbers are so large that they become almost meaningless to the human mind. To put it in perspective, consider that the fastest spacecraft ever built by humanity is the Parker Solar Probe, which, at its maximum speed, reaches about 130 miles per second, or roughly 200 kilometers per second. At that speed, which is achieved only during close passes to the Sun, the Parker Solar Probe could theoretically reach Proxima Centauri in about 6,500 years. The Voyager 1 spacecraft, launched in 1977 and now in interstellar space, is traveling at about 38,000 miles per hour, or roughly 61,000 kilometers per hour. At that speed, it would take more than 70,000 years to reach Proxima Centauri if it were heading in that direction, which it is not. The fastest journey to the outer solar system that humans have achieved was the New Horizons mission to Pluto, which took about 9.5 years to travel 3 billion miles. Proxima Centauri is more than 8,000 times farther away than Pluto. With current technology, reaching Alpha Centauri within a human lifetime is simply impossible. This is the challenge that has haunted space exploration since the beginning. We can see these nearby stars. We can study their light. We can wonder if they have planets, if those planets might harbor life, if conditions there could support human colonization. But the vast gulf of space separating us from them seems insurmountable. And yet, throughout history, what seemed impossible often became possible through innovation, determination, and the refusal to accept limits as permanent. The question is not whether we can reach Alpha Centauri with current technology, because clearly we cannot. The question is whether new technology, new understanding, and new discoveries might change that calculation, and whether the information revealed by the James Webb Space Telescope might be the catalyst that transforms interstellar travel from an impossible dream into an achievable goal. The birth of Webb. To understand why Webb's observations of Alpha Centauri are so significant, we must first understand the telescope itself and the extraordinary journey it took to reach its current position in space. The James Webb Space Telescope is the largest and most powerful space telescope ever constructed, a marvel of engineering that represents decades of planning, innovation, and international collaboration. The idea for Webb began in the 1990s, shortly after the Hubble Space Telescope was launched and began revolutionizing our view of the universe. Scientists and engineers realized that, as remarkable as Hubble was, its capabilities had limits, particularly in observing the infrared portion of the spectrum. They envisioned a successor that would be larger, more sensitive, and specifically designed to observe in infrared light, allowing it to see through cosmic dust, to study the earliest galaxies formed after the Big Bang, and to analyze the atmospheres of distant planets. The telescope was originally called the Next Generation Space Telescope, but it was later renamed the James Webb Space Telescope in honor of James Webb, the NASA administrator who played a crucial role in the Apollo program. Construction began in the early 2000s, but the project faced enormous technical challenges. The primary mirror needed to be much larger than Hubble's, which meant it could not be launched in one piece. Engineers designed a segmented mirror made of 18 hexagonal pieces that would unfold in space. Each segment is coated with a microscopically thin layer of gold, which reflects infrared light more efficiently than other materials. The mirror measures 6.5 meters across, or about 21 feet, giving it more than 6 times the light-collecting area of Hubble. But the mirror was only one challenge. Webb also needed a massive sun shield to keep its instruments cold, because infrared detectors must be extremely cold to function properly. The sun shield is about the size of a tennis court and consists of 5 layers of a special material called kapton. When deployed, the sun shield blocks heat and light from the sun, Earth, and Moon, allowing the telescope's instruments to cool to temperatures as low as -223 degrees Celsius, or about -370 degrees Fahrenheit. The complexity of the design meant that Webb had to be folded up like an intricate piece of origami to fit inside the rocket that would launch it, and then it would have to unfold itself in space with near-perfect precision. There were hundreds of steps in the deployment process, and every single one had to work correctly or the mission would fail. The launch and deployment. The launch date for Webb was delayed multiple times as engineers worked to solve technical problems and ensure that every system was ready. Originally scheduled to launch in 2007, then pushed back repeatedly, Webb finally lifted off on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. The launch was perfect, and Webb began its journey to a special location in space called the Second Lagrange Point, or L2. This point is about 1 million miles from Earth, or roughly 1.5 million kilometers, in the direction away from the Sunday. At L2, the gravitational poles of the Sun and Earth balance in such a way that Webb can orbit this point while using minimal fuel, and the alignment keeps the Sun, Earth, and Moon all on one side of the telescope, allowing the sun shield to block their heat and light simultaneously. The journey to L2 took about 1 month, but during that time, Webb had to execute the most complex deployment sequence ever attempted in space. The sun shield had to unfold layer by layer, each one stretched tight by careful adjustments of dozens of motors and cables. The mirror segments had to swing into position, unfolding like flower petals opening. Then came the painstaking process of aligning all 18 mirror segments so that they worked together as a single perfect mirror. Engineers used tiny actuators behind each segment to adjust their positions with nanometer precision, tilting and shifting them until light from a single star reflected off all 18 segments and converged to a single focused point. This alignment process took months. Then the instruments had to be cooled, calibrated, and tested. Finally, in July 2022, NASA released the first images from Webb, stunning pictures of distant galaxies, nebulae, and exoplanets that immediately demonstrated the telescope's extraordinary capabilities. The images showed details never seen before, revealing the universe in ways that exceeded even the most optimistic expectations. Scientists around the world celebrated, knowing that Webb would transform astronomy for decades to come. The infrared advantage. Webb's ability to observe in infrared light is crucial to understanding why its observations of Alpha Centauri are so important. Infrared light has longer wavelengths than visible light, ranging from about 700 nanometers, just beyond what the human eye can see, to about 1 millimeter. Webb is designed to observe in the near-infrared and mid-infrared portions of this range. There are several reasons why infrared observation is so powerful for astronomy. First, infrared light can penetrate dust clouds that block visible light. Stars form inside dense clouds of gas and dust, and these clouds are opaque to visible light. But infrared light can pass through them, allowing astronomers to see the stars forming inside. Second, distant galaxies are so far away that their light is redshifted by the expansion of the universe, stretching wavelengths from visible light into infrared. To see the earliest galaxies formed after the Big Bang, you must observe in infrared, Third, cool objects like planets, brown dwarfs, and debris disks emit most of their radiation in infrared wavelengths. A planet orbiting another star might be millions of times fainter than its star in visible light, making it nearly impossible to detect. But in infrared light, the contrast is much better, making planets somewhat easier to see. Fourth, molecules in planetary atmospheres absorb and emit infrared light at specific wavelengths, creating spectral signatures that reveal the composition of those atmospheres. By analyzing the infrared spectrum of light passing through a planet's atmosphere during a transit, when the planet passes in front of its star, astronomers can determine what gases are present, potentially including biosignatures like oxygen or methane that might indicate life. For all these reasons, Webb's infrared capabilities make it uniquely suited to studying planetary systems around nearby stars, including Alpha Centauri. Hubble could observe Alpha Centauri, but its visible light observations were limited by the overwhelming brightness of the stars themselves, which made detecting faint planets or other features extremely difficult. Webb's infrared vision changes the game, allowing astronomers to see things around Alpha Centauri that were previously invisible. The search for planets. For decades, scientists have wondered whether Alpha Centauri has planets. Given that the system contains 3 stars, and given what we know about planet formation, it seems likely that planets should exist there. But finding them has proven extraordinarily difficult. The first exoplanet around a Sun-like star was not discovered until 1995, when astronomers detected a massive planet orbiting the star 51 Pegasi. Since then, thousands of exoplanets have been found using various detection methods. The most successful method has been the transit method, where astronomers watch for tiny dips in a star's brightness caused by a planet passing in front of it. This method has been used by missions like Kepler and TESS to discover thousands of planets. However, the transit method requires that the planet's orbit be aligned just right so that it passes between the star and Earth, and the probability of this alignment is small. Another method is radial velocity, where astronomers measure the tiny wobble in a star's motion caused by the gravitational pull of an orbiting planet. This method has been very successful, but is most sensitive to large planets orbiting close to their stars. Direct imaging, where astronomers actually take pictures of planets, is possible only for large planets orbiting far from relatively young, bright stars, because the light from the star overwhelms the faint light reflected or emitted by the planet. For Alpha Centauri, these methods have had limited success. The stars are bright, which makes detecting transits and measuring radial velocities challenging. In 2012, astronomers announced the discovery of a planet around Alpha Centauri b using the radial velocity method. But this discovery was later retracted because the signal turned out to be a false detection caused by data processing artifacts. In 2016, a planet was discovered orbiting Proxima Centauri using radial velocity. This planet, called Proxima Centauri b, is roughly Earth-sized and orbits in the habitable zone of its star, the region where liquid water could exist on the surface. This discovery was incredibly exciting because it meant that the closest star to our solar system has a potentially habitable planet. However, Proxima Centauri is a red dwarf star, much dimmer and cooler than the Sun, and it is very active, producing powerful flares that could strip away a planet's atmosphere. Whether Proxima b is truly habitable remains uncertain. As for Alpha Centauri A and B, the question of whether they have planets has remained open, a tantalizing mystery waiting for better instruments and better techniques. Webb turns to Alpha Centauri. When Webb began science operations in mid-2022, its observing schedule was tightly packed with high-priority targets. Scientists from around the world had submitted proposals for observations, and only a fraction could be accepted. Among the approved programs were observations of Alpha Centauri, specifically designed to search for planets and other features in that system. These observations were conducted in late 2022 and early 2023, using Webb's infrared cameras and spectrographs to study the Alpha Centauri system in unprecedented detail. The observations focused on several goals. First, astronomers wanted to directly image any planets that might be present around Alpha Centauri A and B. Webb's infrared sensitivity and its coronagraphs, special instruments that block the light from a star to reveal faint objects nearby, offered the best chance yet to detect planets if they existed. Second, the team wanted to study the region around the stars for signs of asteroid belts or debris disks, collections of dust and small bodies that indicate past or ongoing planet formation. Third, they hoped to characterize the stars themselves in infrared wavelengths, adding to our understanding of these crucial neighbors. The data from these observations took months to analyze. Astronomers had to carefully process the images, removing artifacts, calibrating the brightness, and searching for any faint points of light that might indicate planets. They used sophisticated algorithms to subtract the overwhelming light from the stars, revealing the fainter structures around them. And then, in the processed data, they saw something. The exact nature of what Webb detected has not been fully disclosed to the public at the time of this writing, because scientific discoveries must be carefully verified before they are announced. And the peer review process ensures that findings are robust and not based on errors or misinterpretations. But reports from the scientific community suggest that Webb has detected features around Alpha Centauri that have profound implications. The rumors speak of possible direct detections of planetary candidates, of evidence for dust structures that suggest planetary systems, and of spectral signatures that hint at complex chemistry in the system. If these findings are confirmed, they would represent one of the most important discoveries in the history of astronomy. What Webb might have seen? Let us consider what Webb might have detected and why it would be so significant. If Webb has directly imaged a planet around Alpha Centauri, A or B, it would be the closest exoplanet ever directly observed, and one of the very few directly imaged planets around a sun-like star. Most directly imaged planets orbit young, massive stars and are giant planets much larger than Jupiter. A planet around Alpha Centauri would likely be smaller, potentially Earth-sized or super-Earth-sized, making it an extraordinary achievement. Direct imaging is important because it allows astronomers to study a planet's light directly, rather than inferring properties from indirect methods. By analyzing the infrared spectrum of the planet's light, scientists can determine its temperature, estimate its size, and potentially detect molecules in its atmosphere. If the planet is in the habitable zone, where temperatures allow liquid water, the discovery would instantly become one of the most important targets for follow-up studies, because it would be close enough for future missions to study in great detail. Another possibility is that Webb has detected a debris disk around one or both of the stars. Debris disks are collections of dust and small rocky bodies, similar to the asteroid belt in our solar system or the Kuiper belt beyond Neptune. These disks form from the collisions of asteroids and comets, and from the gradual grinding down of larger bodies. The presence of a debris disk indicates that solid planet formation has occurred in the system because the asteroids and comets that make up the disk are the leftover building blocks of planets. Studying the structure of a debris disk can reveal the presence of planets because planets gravitationally shepherd the disk material, creating gaps and clumps. If Webb has detected a debris disk around Alpha Centauri with interesting structures, it would strongly suggest the presence of planets, even if the planets themselves have not been directly seen. Yet another possibility is that Webb has detected something unexpected, some feature or phenomenon that was not anticipated, but that provides new insights into the system. Perhaps there are faint companion objects, brown dwarfs, or massive planets that were previously unknown. Perhaps there are unusual spectral features indicating chemical processes or even technosignatures, signs of technology, though this last possibility is extremely speculative and unlikely. Whatever Webb has detected, the key point is that the data is so intriguing that it has generated significant excitement in the astronomical community, and that excitement is driven by the potential implications for interstellar travel. Why Alpha Centauri matters for interstellar travel. Alpha Centauri is not just any star system. It is the closest star system to Earth, and that proximity is of paramount importance for interstellar travel. Any mission to another star will require enormous resources, advanced technology, and many years of travel time. The closer the target, the more feasible the mission becomes. A journey to Alpha Centauri at 4.2 light-years would be challenging but potentially achievable within a human lifetime if technology advances sufficiently. A journey to a star 10 or 20 light-years away would be far more difficult, requiring multi-generational missions or near light-speed travel technologies that are currently purely theoretical. If Alpha Centauri has planets, especially habitable planets, it transforms from an interesting scientific target into a potential destination for humanity's first interstellar mission. The discovery of planets around Alpha Centauri would answer one of the key questions that must be resolved before planning such a mission. Is there somewhere to go? An interstellar mission to a star system with no planets, or with only inhospitable gas giants, would be scientifically interesting but would not offer the possibility of colonization or the establishment of a human presence. But if Alpha Centauri has rocky planets, particularly planets in the habitable zone, the calculation changes entirely. Such planets could potentially support life, or they could be terraformed, transformed over centuries to make them habitable. They could serve as stepping stones for further exploration, as bases from which to launch missions to more distant stars. The presence of habitable planets around Alpha Centauri would provide a tangible goal, a destination that could inspire and justify the enormous effort required to develop interstellar travel technology. Moreover, the existence of planets around Alpha Centauri would provide crucial information for designing an interstellar mission. Knowing the number of planets, their sizes, their orbits, and their compositions would allow mission planners to target specific worlds for exploration. Understanding the structure of the system, including the presence of asteroid belts or debris disks, would help in planning trajectories and avoiding hazards. And if Webb's observations reveal atmospheric compositions, that data would be invaluable for assessing habitability and for planning future missions that might attempt to study those atmospheres in even greater detail, or even to send probes that could transmit data back to Earth. The Breakthrough Starshot Initiative. The idea of sending a mission to Alpha Centauri is not purely theoretical. There is an actual project called Breakthrough Starshot that aims to do exactly that. Announced in 2016, Breakthrough Starshot is a research and development program funded by the Breakthrough Initiatives, a group founded by Russian billionaire Yuri Milner and supported by figures like Stephen Hawking and Mark Zuckerberg. The goal of Starshot is to develop a spacecraft that could reach Alpha Centauri within about 20 years of launch. Given that light takes 4.2 years to travel from Alpha Centauri to Earth, a 20-year journey would mean traveling at roughly 20% of the speed of light, or about 60,000 kilometers per second. This is far faster than any spacecraft has ever traveled. The concept behind Starshot is radically different from traditional spacecraft design. Instead of a large, heavy spacecraft propelled by chemical rockets or even advanced nuclear propulsion, Starshot envisions a fleet of tiny spacecraft, each weighing only a few grams, called starships. These star chips would be equipped with cameras, sensors, and communication equipment, all miniaturized using advanced nanotechnology. Each star chip would be attached to a lightweight reflective sail, a few meters across. The spacecraft would be launched into Earth orbit, and then an array of powerful ground-based lasers would be fired at the sails. The laser light would push against the sail, accelerating the spacecraft to 20% of light speed over a period of minutes. Once up to speed, the spacecraft would coast through space, reaching Alpha Centauri in about 20 years. Upon arrival, the spacecraft would fly through the system at high speed, taking pictures and collecting data, and then transmit that data back to Earth using onboard lasers. The data would take 4.2 years to reach Earth, meaning that the total time from launch to receiving data would be about 25 years. The concept is technically feasible in principle, though it faces enormous engineering challenges. The laser array would need to be incredibly powerful, perhaps requiring a square kilometer of solar panels to power it. The sails would need to be extraordinarily lightweight and reflective, and would need to survive the intense laser light without melting or tearing. The star chips would need to be able to operate in the harsh environment of interstellar space, enduring cold, radiation, and micrometeorite impacts. The navigation would need to be precise enough to aim the spacecraft at Alpha Centauri over distances of trillions of miles. And the communication system would need to be able to transmit data across 4.2 light-years using a tiny laser with very limited power. Despite these challenges, the Breakthrough Starshot team believes the mission is achievable with current or near-future technology, and they are working on developing prototypes and testing key systems. How Webb's discoveries impact Starshot. Now we can see why Webb's observations of Alpha Centauri are so important for Breakthrough Starshot and for the future of interstellar travel. Starshot is planning to send probes to Alpha Centauri, but the mission design depends critically on what is there. If there are planets, especially habitable planets, the mission can be targeted to fly by those planets, maximizing the scientific return. If there are no planets, or if the planets are in orbits that make flybys difficult, the mission design might need to be adjusted, or the target might need to be reconsidered. Webb's data provides the information needed to make these decisions. If Webb has detected planets, Starshot's team now has specific targets to aim for. They can calculate the best trajectories, the optimal timing for launch, and the types of instruments the star chips should carry to study those planets during the flyby. If Webb has detected a debris disk with interesting structures, that data can inform the design of the navigation and shielding systems, because the spacecraft will need to avoid or survive impacts with dust grains traveling at 20% of light speed. Even a tiny particle would hit with enormous energy at that velocity, potentially destroying the spacecraft. Understanding the distribution of material in the system is crucial for planning a safe path. Moreover, Webb's observations can motivate and justify the enormous investment required for Starshot. The project will cost hundreds of millions or even billions of dollars to develop, build, and operate. Securing that funding requires demonstrating that the mission is scientifically valuable and that there is a compelling target. The discovery of planets around Alpha Centauri, especially potentially habitable planets, provides that justification. It shows that interstellar travel is not just a philosophical exercise, but a practical endeavor with concrete goals. The data from Webb could also accelerate the timeline for Starshot. If the discoveries are sufficiently exciting, they could generate public interest and political support that speeds up funding and development. Conversely, if Webb's observations show that Alpha Centauri lacks interesting features, Starshot might need to reconsider its target, potentially looking at more distant stars that are known to have planets, though that would make the mission significantly more challenging. The physics of interstellar travel. To truly appreciate the challenge and the potential of reaching Alpha Centauri, we need to understand the fundamental physics involved in interstellar travel. The primary obstacle is speed. Traveling 4.2 light-years in a reasonable amount of time requires velocities that are a significant fraction of the speed of light. As mentioned, Breakthrough Starshot aims for 20% of light speed, which would allow a journey time of about 20 years. But achieving such speeds with any macroscopic object is incredibly difficult because of the energy requirements. The kinetic energy of an object increases with the square of its velocity, meaning that doubling the speed requires 4 times as much energy. At relativistic speeds, approaching the speed of light, the energy requirements become even more extreme due to relativistic effects. The amount of energy needed to accelerate a 1 kilogram object to 20% of light speed is roughly equivalent to the energy content of several megatons of TNT. For a large spacecraft weighing thousands of kilograms, the energy requirements become astronomical, far beyond what any current propulsion system can provide. This is why Starshot's approach of using tiny, lightweight spacecraft is so important. By reducing the mass to just a few grams, the energy required becomes manageable, at least in principle. Another challenge is propulsion. Traditional rockets work by expelling mass at high velocity, and the change in the rocket's velocity is determined by how fast the exhaust is expelled and how much of the rocket's mass is fuel. Chemical rockets expel exhaust at a few kilometers per second, which limits the maximum speed that can be achieved. Ion engines and other advanced propulsion systems can expel exhaust much faster, but they still face limits. To reach 20% of light speed using traditional propulsion would require carrying an enormous amount of fuel, so much that the fuel itself would add mass, requiring even more fuel to accelerate it, leading to a vicious cycle. This is why Starshot uses laser propulsion, where the energy source is external, on Earth, and the spacecraft carries no fuel at all. The laser light pushes the sail, accelerating it without adding mass. There are also challenges related to time. At 20% of light speed, relativistic time dilation becomes noticeable, though not extreme. The spacecraft's clock would run slightly slower than clocks on Earth, but the effect would be small. However, even at this speed, the journey takes 20 years, and the signals take another 4 years to return, meaning that the people who launch the mission will be 25 years older when they receive the first data. For a mission to a more distant star, the timescales become prohibitive unless even higher speeds can be achieved. The challenges of communication. Communication across interstellar distances presents another formidable challenge. When a spacecraft is millions of miles from Earth, it can still communicate relatively easily using radio signals. The signals take minutes or hours to travel, and the signal strength decreases with distance. But large antennas on Earth can still detect the faint signals. However, at distances of light years, the signal strength becomes incredibly faint, decreasing with the square of the distance. A signal from Alpha Centauri would be about 10 trillion times weaker than a signal from the same transmitter at the distance of Mars. To overcome this, the spacecraft needs a very powerful transmitter, a highly directional antenna, and Earth needs very large, sensitive receivers. Breakthrough Starshot plans to use lasers for communication because laser beams can be focused into very narrow beams, concentrating the signal. Even so, the laser on the starship would need to be aimed with extraordinary precision to hit Earth from 4 light-years away, and the beam would spread over the journey, so only a tiny fraction of the light would reach Earth. Detecting that faint laser signal against the background noise would require large telescopes on Earth equipped with sensitive detectors. Another issue is the delay. At 4.2 light-years, any message sent from the spacecraft takes 4.2 years to reach Earth, and any command sent from Earth takes 4.2 years to reach the spacecraft. This means that the spacecraft must be largely autonomous, capable of making decisions and adjusting its instruments without waiting for instructions from Earth. If the spacecraft encounters an unexpected situation, such as a planet in an unanticipated orbit, it will need to react on its own. This requires sophisticated onboard artificial intelligence, which must be lightweight and low power. These communication challenges highlight the importance of Webb's observations. If we know ahead of time what is around Alpha Centauri, the mission can be better planned, reducing the need for on-the-fly adjustments and increasing the chances of success. The more we know before the mission launches, the better we can design the spacecraft and its operations. The search for habitable worlds. One of the most profound questions driving the study of Alpha Centauri is whether any planets in the system could support life. Habitability depends on many factors, but the most important is the presence of liquid water. Water is essential for all known life, and the conditions that allow liquid water to exist on a planet's surface define the habitable zone around a star. The habitable zone is the region where the star's heat is just right, not too hot and not too cold, so that water can remain liquid. For a star like the Sun, the habitable zone extends from roughly the orbit of Venus to the orbit of Mars, though the exact boundaries depend on factors like atmospheric composition. For Alpha Centauri A, which is slightly larger and brighter than the Sun, the habitable zone would be slightly farther out. For Alpha Centauri B, which is slightly smaller and dimmer, the habitable zone would be slightly closer in. If a planet is found in the habitable zone of either star, it would immediately become one of the most important targets for study. But being in the habitable zone is not sufficient for habitability. The planet also needs an atmosphere, because without an atmosphere, water would either freeze or evaporate. The atmosphere must have the right composition and pressure to maintain liquid water. It should probably contain greenhouse gases like carbon dioxide or methane to help trap heat. It should not be too thick like Venus's crushing atmosphere or too thin like Mars's tenuous atmosphere. The planet's size matters too. If the planet is too small, it will not have enough gravity to hold onto an atmosphere. If it is too large, it might be a gas giant with no solid surface. The ideal size is probably somewhere between half and twice the size of Earth. The planet also needs protection from harmful radiation. Stars emit ultraviolet light and X-rays, which can damage biological molecules. Earth's ozone layer protects life from much of the Sun's ultraviolet radiation, and Earth's magnetic field deflects charged particles from the solar wind. A habitable planet around Alpha Centauri would need similar protections. The star's activity level is important too. Stars like the Sun have cycles of activity, with periods of intense sunspot activity and flares, but the activity is relatively mild. Red dwarf stars like Proxima Centauri are much more active, producing powerful flares that could strip away a planet's atmosphere over time. Alpha Centauri A and B are relatively calm stars, similar to the Sun, which bodes well for habitability. The potential for life. If a planet in the habitable zone exists around Alpha Centauri, the next question is whether life could have arisen there. On Earth, life began relatively soon after the planet's surface cooled enough to support liquid water, about 4 billion years ago. This suggests that life might arise fairly easily, given the right conditions. The ingredients for life, complex organic molecules, are common in space. Amino acids and other organic compounds have been found in meteorites and in interstellar clouds. The chemical reactions that could lead to the first self-replicating molecules can occur in various environments, from warm tidal pools to deep-sea hydrothermal vents. If a planet around Alpha Centauri has had liquid water for billions of years, it is conceivable that life could have arisen there independently of Earth. Whether that life would be intelligent is another question. On Earth, life existed for billions of years before complex multicellular organisms evolved, and intelligence emerged only very recently, less than 1 million years ago. Many factors influence the evolution of intelligence, and it is possible that most planets with life have only simple microbes. However, the possibility of finding even microbial life on another world would be one of the most significant discoveries in history, answering the ancient question of whether we are alone in the universe. Searching for signs of life on exoplanets is incredibly difficult with current technology, but it is not impossible. One approach is to look for biosignatures, signs of life, in the planet's atmosphere. Certain combinations of gases, such as oxygen and methane together, are considered potential biosignatures because they would not coexist in large quantities without biological processes constantly replenishing them. On Earth, oxygen is produced by photosynthesis, and methane is produced by certain microbes. If we detected both gases in the atmosphere of an exoplanet, it would be a strong hint that life might be present. Webb's infrared capabilities are ideal for studying exoplanet atmospheres because molecules absorb infrared light at specific wavelengths, creating spectral features that can be analyzed. If Webb has detected a planet around Alpha Centauri and has obtained spectral data, astronomers may be able to determine its atmospheric composition. If biosignatures are detected, it would be a stunning discovery, though scientists would be very cautious about claiming the detection of life without ruling out all non-biological explanations. The engineering of interstellar probes. Even if Alpha Centauri has habitable planets, getting there remains a monumental engineering challenge. Let us explore in more detail how breakthrough starshot and similar concepts plan to overcome the obstacles. The laser propulsion system at the heart of starshot requires an enormous array of lasers, perhaps covering a square kilometer on the ground. Each laser would contribute a small amount of power, but together they would generate a combined beam of perhaps 100 gigawatts, comparable to the output of 100 large power plants. This beam would be focused on the sail of the tiny spacecraft, which is only a few meters across, requiring extraordinary precision. The laser array would need to track the spacecraft as it accelerates, adjusting the beam direction in real time to keep it centered on the sail. The sail itself must be incredibly thin and lightweight to minimize mass, but also strong and reflective enough to withstand the intense laser light without tearing or melting. Current research is exploring materials like graphene or specially engineered thin films that might meet these requirements. The sail would likely be made of multiple layers, with the outer layer designed to reflect the laser light and inner layers providing structural support. The star chip payload would be attached to the center of the sail and would contain cameras, spectrometers, a small computer, and a laser for communication. All of this must fit into a package weighing only a few grams, which requires extreme miniaturization. Modern smartphones contain remarkably powerful computers and cameras, and similar technology, scaled down even further, could be used in the star chips. The power source for the star chip is a challenge. Solar panels would not work because the spacecraft will be so far from the sun that sunlight will be too faint. Instead, the star chips might use small radioactive power sources, similar to the radioisotope thermoelectric generators used in deep space probes, but much smaller and lighter. Alternatively, they might store energy during the laser acceleration phase using advanced batteries or capacitors, and then ration that energy carefully over the 20-year journey. Radiation protection is another concern. Interstellar space is filled with cosmic rays, high-energy particles that can damage electronics. Shielding against cosmic rays is difficult because shielding adds mass, but some protection can be achieved by designing radiation-hardened electronics and by using redundancy. So if one component fails, others can take over. The navigation problem. Navigating to Alpha Centauri over a distance of 4.2 light-years requires extraordinary precision. A small error in the initial trajectory could cause the spacecraft to miss the star system entirely. At 20% of light speed, the spacecraft travels about 60,000 kilometers every second, or roughly the circumference of Earth every second. Over a journey of 4.2 light-years, even a tiny angular error would result in missing the target by millions of kilometers. The spacecraft must be aimed with an accuracy of better than a millionth of a degree. Achieving this precision requires very accurate knowledge of the spacecraft's position and velocity, and very precise control over the initial trajectory. The laser propulsion system must accelerate the spacecraft in exactly the right direction, and the timing of the laser pulses must be controlled with extreme accuracy. Once the spacecraft is up to speed and coasting, there is no way to make major course corrections because the spacecraft has no fuel for thrusters. It might have small flaps or vanes on the sail that can be adjusted to make tiny changes in direction by catching stray light, but these would provide only minimal control. This means that the initial launch and acceleration must be nearly perfect. During the journey, the spacecraft's navigation system can use star sightings to determine its position and velocity. By measuring the angles to known stars and comparing them to expected values, the spacecraft can calculate where it is and make small adjustments if its solar sail or other mechanisms allow. As it approaches Alpha Centauri, it will need to identify the star system and aim its instruments at the targets of interest, such as planets. This requires sophisticated onboard software capable of processing images, identifying objects, and executing pre-programmed observation sequences. The flyby will happen very quickly. At 20% of light speed, the spacecraft will cross the Alpha Centauri system in a matter of hours or less, depending on the exact trajectory. During that brief window, it must collect as much data as possible. Cameras must take pictures, spectrometers must record spectra, and all the data must be stored on board for later transmission. There is no time for communication with Earth, no opportunity to receive instructions. Everything must be planned in advance and executed autonomously. The data return. After the flyby, the spacecraft's primary mission is to transmit the data back to Earth. This is perhaps the most challenging part of the entire mission. The spacecraft is traveling away from Earth at 20% of light speed, and the distance is increasing by about 60,000 kilometers every second. The communication system must transmit data across 4.2 light-years using a tiny laser powered by the spacecraft's limited energy reserves. The data rate will be very low, probably only a few bits per second, meaning that it could take months or years to transmit all the data collected during the flyby. The laser beam must be aimed at Earth with extraordinary precision. Over a distance of 4 light-years, even a tiny angular error would cause the beam to miss Earth entirely. The spacecraft must know Earth's position very accurately, accounting for Earth's orbit around the Sun and the fact that Earth is moving at about 30 kilometers per second in its orbit. By the time the signal travels 4.2 years to reach Earth, Earth will have moved billions of kilometers, and the spacecraft must aim at where Earth will be, not where it was. On Earth, large telescopes must be prepared to receive the signal. The laser light from the spacecraft will be incredibly faint, comparable to detecting a single candle flame from thousands of kilometers away. Sensitive detectors and sophisticated signal processing will be needed to extract the data from the background noise. Multiple telescopes around the world might be coordinated to maximize the chances of detecting the signal and to provide redundancy in case one telescope has bad weather or technical problems. If the mission succeeds, the data transmitted back to Earth could include detailed images of planets, spectra of their atmospheres, measurements of magnetic fields, temperatures, and compositions, and perhaps even the first close-up views of worlds orbiting another star. These data would be invaluable for planning future missions and for understanding the nature of planetary systems around other stars. If Starshot sends a fleet of starships, which is the plan, then multiple spacecraft could fly through the system on different trajectories, providing different perspectives and increasing the total amount of data collected. Some could target planets, others could study the stars themselves, and others could investigate other features, like asteroid belts or dust clouds. The redundancy would also protect against the failure of individual spacecraft, which is likely given the many hazards of interstellar travel. The role of Webb in future missions. Webb's observations of Alpha Centauri will not only inform breakthrough starshot, but will also guide the design of future missions and future telescopes. If Webb detects planets, the next step will be to study those planets in even greater detail. Future space telescopes, some already in the planning stages, will be designed to take direct images of Earth-like planets around nearby stars and to analyze their atmospheres for biosignatures. One such concept is the Large UV Optical Infrared Surveyor, or LUVOIR, a proposed space telescope with a mirror much larger than Webb's, potentially up to 15 meters in diameter. LUVOIR would be able to directly image planets in the habitable zones of nearby stars and would have the sensitivity to detect biosignatures in their atmospheres. Another concept is the Habitable Exoplanet Observatory, or HabEx, which would use a star shade, a large flower-shaped screen flown in formation with the telescope, to block the light from a star and reveal the faint planets nearby. These missions are still in the planning stages and would not launch for many years, but they represent the next generation of exoplanet science. Webb is a pioneering instrument, opening the door to discoveries that future missions will explore in detail. If Webb finds a planet around Alpha Centauri, that planet will become a priority target for LUVOIR or HabEx. These future telescopes could study the planet's seasons, its weather, the distribution of land and water if it has them, and the composition of its atmosphere with enough precision to search for clear signs of life. They could even potentially detect the presence of vegetation, which has a distinctive spectral signature called the red edge, caused by the way chlorophyll reflects near-infrared light. This is speculative, but the point is that Webb's discoveries set the stage for a cascade of follow-up studies that could last for decades. In addition to space telescopes, ground-based telescopes are also advancing rapidly. The next generation of extremely large telescopes, such as the 30-meter telescope and the European Extremely Large Telescope, will have mirrors much larger than current ground-based telescopes, and they will use adaptive optics to correct for atmospheric blurring, achieving image quality comparable to space telescopes. These instruments will also be able to study exoplanets around nearby stars, complementing the observations from space. The timescale for interstellar travel. When we think about interstellar travel, we must also consider the timescales involved, not just for the journey but for the entire project from conception to completion. Breakthrough Starshot was announced in 2016, but the technology required is still in the early stages of development. The project aims to send a mission to Alpha Centauri within the next 20 to 30 years, meaning a launch in the 2040s or 2050s, with data returning in the 2060s or 2070s. This timeline assumes that the necessary technology can be developed and tested, that funding remains available, and that no insurmountable obstacles are encountered. However, history shows that large space projects often take longer than initially planned. The James Webb Space Telescope was proposed in the 1990s. Construction began in the 2000s, and it launched in 2021, more than 2 decades after the original optimistic timelines. Breakthrough Starshot could follow a similar trajectory, with delays caused by technical challenges, funding issues, or the need to test and refine the technology. Even with these delays, a mission could potentially launch by the middle of this century. If the journey takes 20 years and the data transmission takes another 4 years, the first results could be received by the 2080s. This means that people alive today, especially children and young adults, have a realistic chance of seeing the results of humanity's first mission to another star system. This is an extraordinary thought, that within a single human lifetime, we might send probes to Alpha Centauri and receive detailed data from a world orbiting another star. It also means that the discoveries made by Webb right now are directly relevant to a mission that could happen within our lifetimes. The data Webb provides will inform the mission design, the choice of targets, and the scientific instruments carried by the probes. In this sense, Webb is not just a telescope for studying the distant universe. It is a scout, a pathfinder, preparing the way for humanity's first steps into interstellar space. The broader impact on humanity. The idea of reaching Alpha Centauri and the discoveries made by Webb that might make that journey meaningful have implications far beyond science and technology. They touch on fundamental questions about humanity's future, our place in the cosmos, and the choices we make as a species. For most of human history, our ancestors lived in small communities, aware only of the world immediately around them. Over time, exploration expanded our horizons, first across continents, then across oceans, and eventually to the moon and the planets of our solar system. Each expansion has broadened our perspective, showing us that the world is larger and more diverse than we previously imagined. Interstellar travel represents the next great expansion, a leap not just to nearby worlds, but to other stars, other solar systems, potentially other civilizations. The knowledge that there are planets around Alpha Centauri, especially habitable planets, could inspire a sense of connection to the cosmos and a motivation to overcome the challenges that divide us on Earth. If we know there are worlds we could reach, worlds that might be homes for future generations, it provides a tangible goal, a frontier that can capture the imagination and drive technological and social progress. Throughout history, the promise of new frontiers has motivated exploration, innovation, and cooperation. The space race of the 1960s, driven by competition but also by the dream of reaching the moon, led to technological advances that have benefited all of humanity, from satellite communications to medical imaging to materials science. A renewed focus on interstellar travel could have similar benefits, driving advances in propulsion, energy, materials, computing, and many other fields. Moreover, the perspective gained from knowing that we are part of a larger cosmos, that there are other worlds and perhaps other life forms, can change how we see ourselves and each other. The famous photograph of Earth, taken from the moon, the Earthrise image, and the pale blue dot image taken by Voyager from beyond the solar system, have had a profound impact on how people think about our planet. They show Earth as a small, fragile world in the vastness of space, a perspective that emphasizes the need to protect our environment and to work together as a species. The discovery of habitable planets around Alpha Centauri could have a similar effect, showing us that Earth is not unique, that the conditions for life exist elsewhere, and that humanity's future may lie not just on this one planet, but on many worlds across the galaxy. The ethical considerations. As we contemplate sending missions to Alpha Centauri and potentially discovering habitable worlds or even life there, we must also consider the ethical dimensions of interstellar exploration. If we find a planet with life, even microbial life, do we have the right to interfere with it? Do we have a responsibility to protect it? On Earth, we have seen the consequences of contact between different human societies, often resulting in the destruction of indigenous cultures and ecosystems. The same concerns apply, perhaps even more strongly, to contact with alien life. The concept of planetary protection is already well established in space exploration. NASA and other space agencies follow strict protocols to avoid contaminating other worlds with Earth life, which could interfere with the search for native life and could potentially harm alien ecosystems. Missions to Mars, for example, are carefully sterilized to minimize the risk of carrying Earth microbes to the Martian surface. For an interstellar mission, these concerns are even more significant. If we send probes to Alpha Centauri and they crash on a planet with life, they could introduce Earth organisms that might outcompete or destroy native life. While the Starshot probes are small and fast-moving, making it unlikely they would land intact, the risk is not zero. And future missions that might include landers or sample return missions would face even greater ethical scrutiny. There are also questions about the rights of future generations. If we discover habitable planets, do we have the right to claim them for humanity? Or should we leave them untouched for future generations to decide what to do with them? Do we have a responsibility to preserve them as natural reserves, or do we have a right to terraform them, to transform them into Earth-like worlds, even if that means destroying any existing ecosystems? These are difficult questions without easy answers. They require careful thought and broad societal debate. As we move closer to the reality of interstellar travel, these ethical considerations will become increasingly important, and we will need to develop frameworks and principles to guide our actions. The discoveries made by Webb, by revealing what exists around Alpha Centauri, will make these ethical questions more immediate and concrete, shifting them from abstract philosophy to practical policy. The concept of a generation ship. While Breakthrough Starshot focuses on tiny, fast-moving probes, there is another approach to interstellar travel that has been discussed for decades: the generation ship. A generation ship is a large spacecraft that travels much more slowly than the Starshot probes, perhaps at only a few % of the speed of light, but carries a crew of humans who would live and die during the journey, with their descendants eventually arriving at the destination. The journey to Alpha Centauri at a few % of light speed would take more than a century, meaning that multiple generations would be born, live their lives, and die on the ship. This concept raises profound questions. What would it be like to live your entire life on a spacecraft, never setting foot on a planet, knowing that you are part of a journey that began before you were born and will continue after you die? How would such a society function? What would motivate the crew to maintain the ship and continue the mission across generations? How would they deal with the psychological and social challenges of confinement and isolation? Various proposals for generation ships have been put forward, ranging from rotating cylinders that create artificial gravity through centrifugal force to hollowed-out asteroids that provide natural shielding from radiation. The ship would need to be entirely self-sufficient, with systems for growing food, recycling air and water, generating power, and maintaining all the technology needed to keep the crew alive and healthy. It would need to carry a large enough population to maintain genetic diversity and to provide a stable society, probably at least a few thousand people, and possibly tens of thousands. The engineering challenges of building such a ship are enormous, far beyond our current capabilities. The energy required to accelerate even a relatively small generation ship to a few % of light speed is staggering, requiring energy sources far more advanced than anything we have today. Fusion propulsion, antimatter propulsion, or other speculative technologies would be needed. The cost would be astronomical, likely trillions of dollars or more, and the project would require international cooperation on a scale never before achieved. Despite these challenges, the concept of generation ships remains appealing because it offers the possibility of establishing a human presence on another world, not just sending robotic probes. If Alpha Centauri has habitable planets, a generation ship could carry colonists who would establish a new human society, a new branch of humanity, living on a world orbiting another star. This would be the ultimate expression of humanity's exploratory spirit, a commitment to spreading life and consciousness across the galaxy. The role of artificial intelligence. As we think about interstellar missions, whether robotic probes or generation ships, artificial intelligence will play a crucial role. For robotic missions like Starshot, the probes must be largely autonomous, making decisions and adjusting their operations without waiting for instructions from Earth, which would take more than 4 years to arrive. Advanced AI will be needed to navigate, to identify targets, to prioritize observations, and to respond to unexpected situations. For generation ships, AI could assist the crew in many ways, from managing life support systems to maintaining the ship's technology, to providing education and entertainment. AI could also serve as a repository of knowledge, ensuring that information is not lost across generations, and that the crew retains the skills needed to complete the mission. There are also more speculative ideas, such as sending AI instead of humans. An AI probe could be much more compact and durable than a crewed mission, and it would not require life support or protection from radiation. An advanced AI could explore the Alpha Centauri system in great detail, perhaps even constructing additional probes or robots on site using local materials, allowing it to explore not just the planets but also moons, asteroids, and other objects in the system. Such a mission might sound like science fiction, but the rapid pace of AI development suggests that within a few decades, we may have AI capable of handling the complexities of interstellar exploration. Of course, this raises its own ethical and philosophical questions. If we send AI to Alpha Centauri, does it represent humanity in any meaningful way? Or is it just a tool, a machine, carrying out pre-programmed tasks? If the AI becomes sufficiently advanced, could it develop its own goals and priorities? And should we grant it any form of rights or autonomy? These questions are part of a broader debate about the nature of intelligence, consciousness, and the moral status of artificial beings, a debate that is becoming increasingly urgent as AI technology advances, the inspiration for new generations. One of the most important impacts of Webb's discoveries and the prospect of missions to Alpha Centauri is the inspiration they provide for young people. Throughout history, great achievements in exploration and discovery have inspired generations to pursue careers in science, engineering, and exploration. The Apollo program inspired countless people to become scientists, engineers, and astronauts, and the images and discoveries from Hubble have inspired a new generation to study astronomy and space science. Webb's images have already captured the public imagination, showing the universe in stunning detail and beauty. If Webb's observations of Alpha Centauri reveal planets, especially potentially habitable planets, the impact could be even greater. Young people today could grow up knowing that there are worlds around our nearest star, worlds that humanity might one day reach, and that knowledge could motivate them to contribute to that goal. The mission to Alpha Centauri, whether it happens in the 2040s or later, will require decades of work by thousands of scientists, engineers, and technicians. It will require advances in many fields, from materials science to photonics to computer science to propulsion technology. Young people entering these fields today, inspired by Webb's discoveries, could be the ones who make the mission a reality. Moreover, the challenges of interstellar travel require not just technical skills, but also creativity, collaboration, and perseverance. These are qualities that education systems aim to develop, and the goal of reaching another star provides a tangible, inspiring context for learning. Students studying physics can see how their knowledge applies to calculating trajectories and energy requirements. Students studying engineering can see how their skills could be used to design spacecraft and propulsion systems. Students studying biology can see how understanding life on Earth helps us search for life on other worlds. The dream of interstellar travel, made more real and immediate by Webb's discoveries, can serve as a powerful educational tool, motivating young people to engage deeply with science and technology. The international collaboration. Interstellar travel is a challenge so great that it will likely require international collaboration on an unprecedented scale. No single nation has the resources or the expertise to undertake such a mission alone. The International Space Station provides a model for how nations can work together on large space projects. With the United States, Russia, Europe, Japan, and Canada all contributing modules, equipment, and crews, an interstellar mission would need similar or even greater levels of cooperation. The Breakthrough Starshot initiative, while privately funded, has involved scientists and engineers from around the world, and any full-scale mission would benefit from contributions from multiple countries. Different nations could contribute different components, such as laser arrays, spacecraft, tracking stations, or data analysis. The cost could be shared, making the mission more affordable for each participant. Moreover, the scientific return from such a mission would benefit all of humanity, not just the countries directly involved. The knowledge gained about Alpha Centauri, about exoplanets, and about the techniques for interstellar travel would be shared openly, advancing science globally. International collaboration also reduces the risks associated with the mission. If one country's technology fails, others can provide backups. If political changes in one country threaten funding, others can step in to keep the project going. The long timescales involved in interstellar missions mean that political continuity is a challenge, and international collaboration can provide stability across changes in government. There are challenges to international collaboration as well, including differences in goals, priorities, and approaches, as well as legal and regulatory issues related to space exploration. Treaties governing the use of outer space, such as the Outer Space Treaty of 1967, establish principles like the prohibition of national appropriation of celestial bodies and the peaceful use of space. Any interstellar mission would need to operate within these frameworks, and as we move closer to actually reaching other stars, the international community will need to develop new agreements addressing issues specific to interstellar exploration. The economics of space exploration. The cost of interstellar travel is difficult to estimate, but it will certainly be enormous. Breakthrough Starshot has estimated that the development and deployment of their system could cost several $billion, including the construction of the laser array, the development and testing of the star chips and sails, and the operation of the mission over the decades it will take to reach Alpha Centauri and transmit data back. This is a substantial sum, but it is comparable to the cost of other large scientific projects, such as the Large Hadron Collider or the James Webb Space Telescope itself. For a generation ship or other crewed mission, the cost would be orders of magnitude higher, potentially reaching into the trillions of dollars. This raises the question of whether such an investment is justified. In purely economic terms, there is no short-term financial return on investment from interstellar travel. The mission will not generate profits, discover valuable resources that can be brought back to Earth, or create products that can be sold. The benefits are primarily scientific and inspirational, and they accrue over the long term. However, history shows that investments in exploration and fundamental science often have unexpected benefits. The space program has led to technologies that have become part of everyday life, from GPS and satellite television to memory foam and cordless tools. The research and development required for interstellar travel could lead to advances in energy production, materials science, propulsion, computing, and many other areas, and these advances could have applications far beyond space exploration. Moreover, the value of knowledge and inspiration is difficult to quantify, but is nonetheless real. Understanding our place in the universe, answering the question of whether we are alone, and achieving something as monumental as reaching another star are goals that resonate deeply with human aspirations. Many people find meaning and purpose in exploration and discovery, and these intangible benefits are a valid justification for investment. Ultimately, the decision to pursue interstellar travel is not just an economic calculation, but a societal choice about what we value and what kind of future we want to create. The legacy of Webb. The James Webb Space Telescope will operate for many years, continuing to make discoveries across a wide range of astronomical topics. Its design lifetime is about 10 years, though it could potentially operate longer if its systems remain healthy. During this time, Webb will study the earliest galaxies, the formation of stars and planets, the atmospheres of exoplanets, and many other phenomena. Among its many achievements, its observations of Alpha Centauri could be among the most consequential for the future of humanity. If Webb has discovered planets around Alpha Centauri, especially habitable planets, it will be remembered not just as a scientific instrument, but as a turning point, the moment when humanity's journey to the stars shifted from abstract speculation to concrete planning. The data Webb provides will inform decades of follow-up research, guiding the design of future missions and shaping our understanding of our nearest stellar neighbors. Even if Webb does not find planets around Alpha Centauri, its observations will still be valuable, ruling out certain possibilities and focusing the search on other stars. Science advances through both positive and negative results, and knowing what is not there is as important as knowing what is. Webb's legacy will also include the technological innovations developed for its construction and operation. The techniques for building large, segmented mirrors, for deploying complex structures in space, for cooling instruments to cryogenic temperatures, and for processing vast amounts of data are all advances that will benefit future missions. Perhaps most importantly, Webb demonstrates what is possible when humanity commits to a bold vision and works together to achieve it. The telescope is the product of collaboration among NASA, the European Space Agency, and the Canadian Space Agency, involving thousands of scientists, engineers, and technicians from around the world. Its success shows that even the most ambitious goals can be achieved with dedication, creativity, and cooperation. The philosophical meaning. As we reflect on Webb's glimpse of Alpha Centauri and the possibilities it opens for interstellar travel, we are drawn to deeper philosophical questions about meaning, purpose, and the future of humanity. Why do we explore? What drives us to look beyond our immediate surroundings, to seek out new knowledge, to push the boundaries of what is possible? For some, exploration is driven by curiosity, the simple desire to know what is out there, to understand how the universe works, to answer fundamental questions about existence. For others, it is driven by the search for resources, for new places to live, for solutions to problems we face on Earth. For still others, it is driven by a sense of destiny, a belief that humanity is meant to spread across the stars, to become a spacefaring civilization. These motivations are not mutually exclusive, and most people who support space exploration feel some combination of all of them. At a deeper level, the impulse to explore may be part of what it means to be human. Our ancestors migrated out of Africa and spread across the globe, crossing mountains and deserts and oceans, settling in every habitable environment on Earth. That same drive now propels us into space, to the Moon, to Mars, and potentially to other stars. There is something in the human spirit that is not content to stay in one place, that seeks to go farther, to see what lies beyond the horizon. The discovery of habitable planets around Alpha Centauri would give us a new horizon to aim for, a destination that embodies all the dreams and aspirations of exploration. But interstellar travel also raises questions about identity and continuity. If we send a generation ship to Alpha Centauri, the people who arrive will be the descendants of those who launched, living in a society that has been shaped by the unique experience of the journey. Will they still consider themselves part of humanity as a whole? Or will they see themselves as a separate group, a new branch of the human family tree? If we establish colonies on multiple worlds, each shaped by different environments and experiences, humanity might diversify into multiple branches, each adapted to its own world. This could be seen as a natural extension of cultural diversity, or it could be seen as a fragmentation of humanity. These are questions without clear answers, but they are worth contemplating as we stand on the threshold of becoming an interstellar species. The transition from imagination to reality. For most of human history, travel to other stars has been the realm of imagination, of myths, stories, and science fiction. Writers like Jules Verne, H.G. Wells, Arthur C. Clarke, and Ursula K. Le Guin have explored the possibilities and challenges of interstellar travel in their works, inspiring generations of readers and shaping popular culture's understanding of space exploration. Television series like Star Trek and films like Interstellar have depicted interstellar journeys and encounters with alien worlds, often serving as thought experiments exploring what might happen when humanity reaches other stars. These stories have kept the dream of interstellar travel alive, even when the reality seemed impossibly far away. But now, with missions like Breakthrough Starshot in development and discoveries like those from Webb showing us what is actually out there, we are moving from imagination to reality. The transition is gradual, with many steps still to take, but the trajectory is clear. Within the lifetimes of people alive today, we may see the first probes launched toward another star. Within the lifetimes of children born today, we may see the first data returned from those probes, the first close-up images of worlds orbiting Alpha Centauri. This transition from imagination to reality is profound. It changes interstellar travel from an abstract concept into a concrete goal, from something that might happen someday to something that is happening now, in the early stages. It means that the choices we make today, the investments we make in science and technology, the priorities we set for space exploration, will directly shape humanity's future among the stars. The discoveries made by Webb are part of this transition. By revealing what exists around Alpha Centauri, Webb is transforming the star from a point of light in the sky into a real place with real features, a destination that we can begin to understand and plan to reach. This knowledge grounds our aspirations, giving them a factual foundation, and it makes the dream of interstellar travel feel attainable rather than fantastical. The question of time. One of the most poignant aspects of interstellar travel is the relationship with time. Even at the speeds envisioned by Breakthrough Starshot, the journey to Alpha Centauri takes decades, and the data transmission takes additional years. This means that the people who plan and launch the mission will not see the results in their youth. Scientists and engineers working on Starshot today, many in their 30s or 40s, will be in their 60s or 70s when the probes reach Alpha Centauri, if the optimistic timeline is achieved. For a generation ship, the timescales are even longer, with the founders of the mission knowing they will die before the destination is reached. This raises questions about motivation and commitment. Why work on something knowing you may not see the outcome? The answer lies in a broader view of human achievement, recognizing that many of the greatest accomplishments in history have required efforts across generations. Cathedrals in medieval Europe took centuries to build, with architects and workers contributing to projects they knew they would not live to see completed. The planting of forests, the building of infrastructure, the education of children, all are investments in the future, acts of faith that future generations will benefit. Interstellar travel is the ultimate multi-generational project, requiring patience, commitment, and a willingness to work toward goals that transcend individual lifetimes. In this sense, it is a deeply human endeavor, reflecting our capacity to think beyond ourselves, to care about the future, and to act on behalf of those who will come after us. The discoveries made by Webb connect us to this broader timeline. The scientists who built Webb and who are now analyzing its data are contributing to a process that will unfold over decades and centuries, a process that may ultimately lead to humanity becoming a multi-star species. They are part of a chain, receiving knowledge from previous generations and passing it forward to the next, each link essential to the whole. The challenges ahead. Despite the excitement generated by Webb's observations and the progress made by projects like Breakthrough Starshot, there are still enormous challenges ahead, and it is important to acknowledge them honestly. The technological hurdles are immense. Building a laser array powerful enough to accelerate spacecraft to 20% of light speed, while also remaining affordable and safe, is a daunting task. Developing sails that can withstand that intense laser light without melting or tearing requires materials that do not yet exist. Miniaturizing all the necessary electronics, sensors, and communication equipment into a package weighing a few grams is at the edge of what current technology can achieve, and it will require further advances. The navigation and communication challenges are equally formidable, requiring precision and reliability far beyond anything attempted before. There are also scientific uncertainties. We do not yet know enough about the interstellar medium, the thin gas and dust that fills the space between stars, to fully understand how it will affect the spacecraft. Even tiny particles, when hit at 20% of light speed, could damage the spacecraft. We do not know how cosmic rays and other forms of radiation will affect the electronics over a journey of decades. And we do not know what we will find when the probes reach Alpha Centauri. Even with Webb's observations, there will be surprises, and the mission must be designed to handle the unexpected. Funding is another major challenge. Starshot has initial funding from the Breakthrough initiatives, but developing the technology to the point where a full-scale mission can be launched will require billions of dollars. And sustaining that funding over decades will require ongoing public and political support. History shows that space projects can lose funding if priorities change, or if technical problems cause delays and cost overruns. Finally, there are social and political challenges. Interstellar missions require long-term commitment from governments, institutions, and the public, and sustaining that commitment across changes in leadership and shifting priorities is difficult. International collaboration, while beneficial, also introduces complexities in terms of coordination and decision-making. These challenges are not insurmountable, but they are real, and addressing them will require sustained effort, creativity, and perseverance. The potential for discovery. If the challenges can be overcome and a mission to Alpha Centauri succeeds, the potential for discovery is extraordinary. Even a simple flyby mission like Starshot could reveal details about the system that fundamentally change our understanding. If there are planets, we would see their surfaces, their atmospheres, their moons if they have any. We could measure their sizes, masses, and compositions with far greater precision than is possible from Earth. We could search for signs of geological activity, such as volcanoes or tectonic movements, and for signs of water, whether as ice, liquid oceans, or atmospheric vapor. If the planets are in the habitable zone, we could study their climates, their weather patterns, and the distribution of clouds and surface features. The data could reveal whether these worlds are truly habitable, whether they have the conditions necessary for life. If biosignatures are detected in the atmospheres, it would be one of the most significant discoveries in the history of science, proof that life exists beyond Earth. Even if no signs of life are found, the data would be invaluable for understanding planetary systems and for planning future, more advanced missions. We could also study the stars themselves in detail, measuring their temperatures, compositions, magnetic fields, and activity levels. We could observe how the two stars in the binary system interact, how they affect each other, and how their orbital dance influences any planets that might be present. We could study the space environment around the stars, the stellar winds, the magnetic fields, the energetic particles, all of which affect the conditions for life on nearby planets. Beyond planets and stars, we could study the architecture of the system as a whole. Are there asteroid belts, comet clouds, or other structures? How is material distributed throughout the system? Are there signs of recent collisions or other dynamic events? All of this information would help us understand how planetary systems evolve over time and how common systems like Alpha Centauri are in the galaxy. Each piece of data returned from Alpha Centauri would be a treasure, a glimpse of a place no human has ever seen, and each discovery would raise new questions and open new avenues for research. The mission would not end our curiosity but would deepen it, providing the foundation for future missions and future generations of exploration. The vision of a multistellar humanity. Looking even further into the future, beyond the first probes to Alpha Centauri, we can begin to envision a time when humanity is not confined to one star, but is present in multiple star systems. This is the ultimate vision of interstellar travel, a future where humans live on worlds orbiting many stars, where the species has diversified and spread across the galaxy, where Earth is remembered as the home world, but is no longer the only world. Achieving this vision would require not just sending probes, but sending people, or sending AI capable of constructing habitats and perhaps even creating biological life using genetic information carried from Earth. It would require solving problems we have not yet seriously confronted, such as how to sustain a human population far from Earth, how to terraform worlds to make them habitable, and how to govern societies separated by light years of space and years of communication delay. This vision may seem impossibly far in the future, but every great achievement begins with a single step. The first step is sending robotic probes to Alpha Centauri, which could happen within decades. The second step might be sending larger, more capable probes that can land on planets and study them in detail. The third step might be sending supplies and equipment ahead of human colonists, pre-positioning resources on a habitable planet to prepare for their arrival. The fourth step might be sending humans, either on a generation ship or using some future propulsion technology that allows faster travel. Each step builds on the previous one, and each step expands humanity's reach. The presence of habitable planets around Alpha Centauri, if confirmed by Webb and future observations, would make this vision more concrete and more achievable. It would show that the conditions for a second home exist within reach, that the dream of a multistellar humanity is not fantasy, but a plausible future. And the work being done now, the discoveries being made, the technologies being developed, are all part of the foundation for that future. The power of hope. Throughout this exploration, one theme has emerged again and again: hope. Hope that we will find habitable worlds. Hope that we will develop the technology to reach them. Hope that humanity's future includes not just survival, but expansion and flourishing across the galaxy. Hope is a powerful force. It motivates action, inspires creativity, and sustains effort even in the face of daunting challenges. The hope of reaching Alpha Centauri has driven scientists and engineers to devote their careers to projects that may not bear fruit in their lifetimes. It has motivated philanthropists to fund research into interstellar travel. It has captured the imagination of the public, generating enthusiasm and support for space exploration. Webb's observations of Alpha Centauri feed this hope. If Webb has discovered planets, it shows that the targets we hope to reach actually exist. If Webb has revealed features that make the system more interesting and more accessible, it brings the dream of interstellar travel closer to reality. Even if Webb's observations are inconclusive, or if the system proves less hospitable than hoped, the data still represents progress, still advances our understanding, and still moves us forward. Hope is not the same as blind optimism. It does not ignore challenges or difficulties. It acknowledges them, but chooses to focus on possibilities rather than limitations. It recognizes that the future is not fixed, that it is shaped by the choices we make and the efforts we invest. Hope is an active stance, a commitment to working toward a better future even when success is uncertain. In the context of interstellar travel, hope is the belief that humanity can overcome the obstacles, can develop the necessary technology, can cooperate across borders and generations, and can ultimately reach other stars. This hope is grounded in the remarkable achievements of the past, in the fact that we have gone from the first powered flight to landing on the moon in only 66 years, from the first computers filling entire rooms to smartphones that fit in our pockets in a few decades. If we can achieve so much in such a short time, what might we achieve in the decades and centuries ahead? The role of public support. The success of interstellar missions depends not just on scientists and engineers, but on the broader public. Public support influences government funding for space exploration, drives political will to commit resources to long-term projects, and creates a culture that values exploration and discovery. Throughout history, public enthusiasm for space has ebbed and flowed. The Apollo program enjoyed enormous public support, with millions of people watching the moon landings on television and taking pride in the achievement. But interest waned in the decades after Apollo, as the focus shifted to the Space Shuttle and the International Space Station, which were less dramatic and less visibly pioneering. In recent years, public interest in space has been rekindled by missions like those to Mars, by the discoveries of thousands of exoplanets, and by the stunning images from Hubble and now Webb. Private companies like SpaceX have also captured the public imagination with ambitious plans for Mars colonization and reusable rockets. The discovery of planets around Alpha Centauri, especially habitable planets, could further boost public enthusiasm, providing a clear and compelling goal that resonates with people's sense of wonder and adventure. Educators, science communicators, and the media all play crucial roles in building and sustaining public support. By explaining the significance of discoveries in accessible language, by sharing the stories of the people involved, and by conveying the excitement and beauty of exploration, they help the public connect with space exploration on an emotional level. Documentaries, articles, videos, and social media posts about Webb's observations and about projects like Breakthrough Starshot can inspire people, especially young people, to care about space and to support efforts to reach the stars. Public support also takes practical forms, such as contacting elected representatives to advocate for funding for space programs, supporting space-related charities and initiatives, and participating in citizen science projects that allow non-professionals to contribute to research. When the public is engaged and supportive, space exploration thrives. The interconnection of knowledge. One of the remarkable aspects of Webb's observations of Alpha Centauri is how they connect many different fields of knowledge. Understanding what Webb has seen requires expertise in astronomy, astrophysics, planetary science, optics, data processing, and more. Planning a mission to Alpha Centauri requires knowledge of propulsion, materials science, computer science, navigation, communication, and engineering. Thinking about the implications requires philosophy, ethics, sociology, and economics. No single person can be an expert in all these areas, and progress requires collaboration across disciplines. This interconnection of knowledge is a hallmark of modern science. The most interesting and important questions often lie at the boundaries between disciplines, where insights from one field can illuminate problems in another. For example, understanding exoplanet atmospheres requires combining knowledge of chemistry, physics, and biology. Designing interstellar probes requires combining engineering with astronomy to optimize the spacecraft for the specific targets and conditions it will encounter. The ability to bring together diverse expertise is one of the strengths of the scientific community, and it is essential for tackling challenges as complex as interstellar travel. Educational systems that encourage interdisciplinary thinking and collaboration are preparing the next generation to contribute to these efforts. Students who learn to integrate knowledge from multiple fields, who can work in teams with people from different backgrounds, and who can communicate across disciplinary boundaries are the ones who will drive future discoveries and innovations. The beauty of the journey. As we near the end of this exploration, it is worth reflecting on the beauty inherent in the journey toward interstellar travel. There is beauty in the observations themselves, in the images that Webb captures, in the spectra showing the light from distant worlds, in the data that reveals the architecture of other planetary systems. There is beauty in the engineering, in the elegant solutions to complex problems, in the precision and care required to build instruments capable of detecting faint signals across vast distances. There is beauty in the mathematics, in the equations that describe the motion of planets, the propagation of light, the bending of space-time by gravity. There is beauty in the collaboration, in the way people from different nations and cultures work together toward a common goal, setting aside differences to pursue shared aspirations. And there is beauty in the human spirit, in the curiosity that drives us to ask questions, in the courage to pursue difficult goals, in the hope that a better future is possible. The story of Webb's glimpse of Alpha Centauri is a story about all of these forms of beauty, woven together into a narrative that spans light years and decades, that connects the past to the future, that links the work of individual scientists to the destiny of the species. This beauty is not just aesthetic, but is meaningful, reflecting deeper truths about who we are and what we aspire to be. It reminds us that humanity is capable of greatness, that we can achieve things that seem impossible, that we can reach for the stars in both a literal and metaphorical sense. The personal connection. For each individual listening to this story, there is an opportunity to connect personally with the narrative of interstellar exploration. You might never work directly on space missions, never analyze data from telescopes, never design spacecraft, but you are still part of this story because the future of space exploration depends on all of us, not just the experts. You can support space exploration through your interest, your enthusiasm, and your willingness to learn. You can share stories about discoveries like Webb's observations of Alpha Centauri with friends and family, spreading awareness and excitement. You can advocate for science education and for funding for space programs. You can inspire young people by showing them the wonders of the cosmos and encouraging their curiosity. If you are a student, you might be inspired to study science, engineering, or another field that contributes to space exploration. If you are a teacher, you can use space as a context for teaching a wide range of subjects, from physics to history to ethics. If you are a voter, you can consider support for space exploration when choosing candidates and policies. If you are a parent, you can encourage your children to look up at the night sky, to ask questions, and to dream about what might be possible. The journey to Alpha Centauri and beyond is not just a technical challenge, but a collective endeavor, and every person who contributes in their own way is part of the effort. Your connection to the story is personal because it is about the future, and the future belongs to all of us. The unfolding story. As this journey through Webb's glimpse of Alpha Centauri comes to a close, it is important to recognize that the story is far from over. In fact, it is just beginning. The data from Webb is still being analyzed, and new discoveries are likely as scientists continue to study the observations. Breakthrough Starshot is still in the early stages of development, with many technical challenges to overcome before a full-scale mission can be launched. Future telescopes, on the ground and in space, will build on Webb's discoveries, providing ever more detailed views of Alpha Centauri and other nearby star systems. The next decades will be a time of rapid progress in exoplanet science, in propulsion technology, in our understanding of what it takes to reach other stars. The story of interstellar travel is unfolding in real time, with each new discovery, each new development, adding another chapter. We are living through a pivotal moment in human history, a time when the dream of reaching other stars is transitioning from science fiction to science fact. The people alive today are the first generation that can seriously plan missions to other stars, that can design technologies capable of making the journey, that can look forward to seeing data from worlds orbiting other suns. This is an extraordinary privilege and an extraordinary responsibility. What we do now, the choices we make, the priorities we set, will shape the trajectory of humanity for centuries to come. And at the center of this unfolding story is Alpha Centauri, our nearest stellar neighbor, a beacon calling to us across the light years, promising knowledge, adventure, and the possibility of a new home. Webb has given us a glimpse of what waits there, and that glimpse has the power to rewrite the future of space travel, the horizon of possibility. And so, we arrive at the end of this journey together. This exploration of how the James Webb Space Telescope's observations of Alpha Centauri could transform the future of space travel. We have traveled across 4.2 light-years of space, not in body but in mind, considering what Webb might have seen, why it matters, and how it connects to humanity's deepest aspirations. We have explored the technical challenges of interstellar travel, from the physics of propulsion to the difficulties of communication across light years, and we have seen how projects like Breakthrough Starshot are working to overcome these obstacles. We have considered the broader implications, the philosophical questions about our place in the universe, the ethical considerations of contact with alien life, the hope that drives exploration, and the beauty inherent in the quest for knowledge. The central message is this: we stand at a threshold. For the first time in human history, we have the knowledge and the technology to seriously contemplate reaching another star. We know that Alpha Centauri exists, that it is the closest star, and that there are likely planets there. Webb has given us a glimpse, a preview of what awaits us, and that glimpse has the power to inspire, to motivate, and to guide the next steps in our journey toward the stars. The path ahead is long and difficult. There are no guarantees of success. The challenges are immense, and the timeline spans decades or even centuries. But humanity has always been a species of explorers, pushing beyond known boundaries, seeking new horizons, refusing to accept limits as permanent. The discovery of planets around Alpha Centauri, if confirmed, would provide a tangible destination, a place to aim for, a goal that can focus our efforts and inspire our dreams. As you drift toward rest now, let your mind wander among the possibilities. Imagine a future where humanity is not confined to one small planet, but has spread across multiple worlds, where children grow up under alien skies, where the species has become resilient and diverse and enduring. Imagine the moment when the first data arrives from Alpha Centauri, when we see close-up images of worlds we have only dreamed about. Imagine the sense of achievement, the pride, the wonder that will accompany that moment. These imaginings are not idle fantasies. They are visions of a future that is within reach, a future that we are actively building through the work being done today by scientists, engineers, and visionaries around the world. Webb's glimpse of Alpha Centauri is a signpost pointing toward that future, a reminder that the stars are not unreachable, that the cosmos is full of wonders waiting to be discovered, and that humanity's story is far from over. The future of space travel is being written now, in the data flowing from Webb, in the laboratories developing new technologies, in the classrooms where young people are learning about the universe, and in the dreams of everyone who looks up at the night sky and wonders what lies beyond. That future is not predetermined. It will be shaped by choices, by effort, by dedication, and by hope. And you are part of it, connected to this grand narrative by the simple fact that you share this planet, this moment in time, this capacity to wonder and to dream. Sleep well, traveler, knowing that the cosmos is vast and beautiful, that humanity is reaching toward the stars, and that Webb has shown us a glimpse of where we might go and what we might become. The journey to Alpha Centauri has begun, not with rockets and spacecraft yet, but with curiosity, with observation, with the steady accumulation of knowledge that lights the way forward. And when the first probes do launch, when the first data returns, when the first humans perhaps one day set foot on a world orbiting another star, we will look back on this moment, on Webb's glimpse of Alpha Centauri, as the beginning of it all, as the moment when the future of space travel was rewritten and the horizon of possibility expanded beyond anything humanity had previously imagined. Good night.